Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. In this video, we are going to start new topic called fluid bending from solid mechanics. This is an important topic. In this topic, we are going to understand stresses and strains developed in the beams because of the bending moments. If you understand these stresses and strains, it will help us to design beams subjected to variety of loading conditions. So first we need to understand pure bending before understanding bending deformations due to non-uniform bending. So we already know that in solid mechanics, we mostly consider prismatic bars, right? So what is prismatic bar? Prismatic bar means the cross-sectional area remains same across the length, means same cross-sectional area, right? So in prismatic bar, the pure bending means the bending with constant bending moment. I hope you already know about shear force diagrams and bending moment diagrams. So let us take one case of pure bending. Let us take a simply supported beam, a simple beam. So and it is applied with couple M1 at the ends A and B, at the supports A and B. So if you consider the if you take here, the reactive force will be this one like this, and here it will be like this. So this will be zero from horizontal equilibrium, and these two will also get to zero when you apply vertical equilibrium and moment equilibrium. So we only have these couples M1, these couple M1. So if you cut over here, this is method of sections to find bending moment at a section, right? So if you consider this part, we already know that if whole beam is in equilibrium, then every part of the beam will also be in equilibrium, right? So let us take this part. Then you can say that we know about the Sine conventions. For positive cross-sectional area, the positive bending moment at the section will be anti-clockwise, M. So here it is M1. So from equilibrium, we will get M is equals to M1, right? So entire length in entire at every cross-section on entire length, the value of bending moment is constant. That value is given by M1, right? So if you draw bending moment diagram, the bending moment diagram will look like this, right? So this is the case of pure bending. It has constant bending moment on its entire length, right? So now let us take another example of the simple beam. So for this simple beam, the load is applied like this. So if you draw bending moment diagrams by considering method of sections, the bending moment diagram will look like this, right? So this length will be A and this will be A. So if you observe the bending moment diagram, the central region has constant bending moment, and at the edges it is non-uniform. So the beam is in under pure bending in central region and in non-uniform bending at edges, right? So if you observe at the non-uniform bending moment region, the value of shear force is non-zero. At the constant bending moment diagram region, the value of shear force is zero. That is obvious from the relationships which we use while drawing bending moment diagrams. We already know the relationship between shear force and bending moment diagram is given by V is equals to dm by dx, right? So if bending moment is constant, shear force will be is equals to 0 if m of x is constant. So for pure bending case, the value of shear stress should be 0. Now let us move forward. So when you apply movements, the body will have some curvature because of the bending deflections, right? So if this is the beam and this is a cantilever beam, if you consider this is fixed and you are applying load P like this, so see it will deflect like this, right? So it will have some some curvature because it forms some arc, right? It has some curvature, right? It is clearly visible. So we need to derive that expression. So if you consider a small dx length before deformation and after bending deformation, that length is ds, okay? So and it subtends angle d theta at the center. Because it is like for small dx element, it will be like a arc of circle, right? So for arc of circle, there will be center, right? So from that center, subtending angle d theta. So we get rho d theta. Rho is radius for that arc. Rho d theta will be is equals to ds. So we get 1 by rho will be is equals to d theta by ds. We already know rho is radius of curvature. Rho is radius of curvature. Okay. So we get kappa is equals to C for small deflections. ds will be is equals to dx for small deflections. We already know that in civil engineering structures, the structures are designed for small deflections only, for comfortableness, right? For small deflections. So ds will be is equals to ds. So we can write kappa 1 by rho will be is equals to d theta by dx. So this is the relationship which we use, and this k is known as curvature. So if you see, the curvature and radius of curvature are inversely proportional. Let us understand that. See, if it is a straight line, the beam is straight, there is no deformations in the beam, then what is the curvature? Curvature is 0 over here, right? The curvature is 0. See, if you see d theta by dx, the change in angle is also 0, right? So k will be 0. But if you speak about radius of curvature, it is infinite. Okay. See, if you let us draw one diagram to understand this. See, if you consider, this is the initial beam without deflection. After deflection, it is becoming something like this. Okay. So then the radius of curvature is given by this one, rho 1. Okay. So this is like this. And you applied more bending moment, then it will, the curve will be more, right? So it will deform more. So it will become something like this, right? Then if you draw the center of this, the center will be located at here, right? So now the radius of curvature will be rho 2. So if you see, the radius of curvature is decreasing with increase in the deformation, right? So as you increasing the deformation, the radius of curvature is decreasing. But the curvature, how much curve? The more it forms the curve, the more is the curvature. So the curvature should increase, right? So the curvature will increase on increasing the deformation. Okay, here the rho 1 is greater than rho 2. So for a straight line, the curvature is 0, but the radius of curvature is infinite. I hope you understand clearly about curvature and radius of curvature. The sign convention of the curvature. See, you can take any sign conventions, but strictly we should follow one sign convention to avoid confusions. Okay. So if the curvature is looking like this upwards, then it is positive curvature in our sign convention. If it is looking like this, then it is negative curvature. Okay. This is about curvature sign conventions. Now we need to observe few points in pure bending. So this is the undeformed beam, and after application of bending moments, after application of the load, it is undergoing pure bending. On pure bending, the deformed shape is looking like this. So the first point, the first observation is plane sections remain plane before and after bending. See, if you see this plane section, this is plane before bending. After bending also, if you see over here, this is plane again. This can happen only in the case of pure bending. If you take non-uniform bending, there will be shear force. Because of that, the warping will occur. Warping means the plane will go out of the plane after deformation. That is known as warping. So in pure bending, the plane sections will remain plane. You can observe from this also. This is live example. See, if you apply end movements, opposite movements, then it will be under pure bending, right? So I am applying like this. So this is the deformed shape. If you observe deformed shape, if you see this cross section, this cross section is plane, right? So before deformation also it is plane. After deformation also it is plane, right? So after deformation also it is plane. So the plane sections will remain plane in case of pure bending. Let us go to the next point. Comprises tension and compression. So if you observe this plane section, initially the line is like this. After the deformation, the line became like this. So the line became something like this. So for if you apply bending moments like this, okay. If you apply bending moments like this, the curvature will go upwards, right? Then this line will become like this. So initially the particles are here. Now they gone to here. So here also they gone to here, right? So the initial length is this much, but the final length is decreased, right? So the particles go on to here. So they compress it under top, at the top area, they are under compression. If you go to the bottom portion, the length is increased, right? So here the particles move to here. So the bottom portion for this bending moments, the bottom portion is in tension. So each plane consists of tension and compression in longitudinal direction, okay? So if you see at one position, it is compression, at another position, it is tension. So and the compression is maximum at the top and it is decreasing eventually, right? The tension is maximum at the top and it is decreasing eventually. So there should be one point where the change in length should be zero, right? That is clearly visible. So there should be one point where the change in length should be zero. So that points, if you if you take one plane section, that will be a line like this, right? For that plane. And if you take every plane, every cross section and consider, draw those lines and connect those lines, connect those all lines, then you will get one surface. So that surface is known as neutral surface. And along the longitudinal axis, if you draw the axis through this neutral surface, on this neutral surface, then that is known as neutral axis. Okay. So with this, we end today's lecture. I hope you understood clearly. If you liked the lecture, do subscribe to our channel, Ninepointer. Thank you.